Want to learn the conservation of energy and thermodynamics in its maritime applications? Let us listen to the discussion of Group 2.
Good day everyone. Today we're going to be talking about conservation of energy in thermodynamics and its maritime applications. So energy conservation expressed through the first law of thermodynamics states that energy cannot be created or destroyed, only transformed or transferred between systems. This principle provides the foundation for analyzing and optimizing all thermodynamic processes. In the maritime industry, it is especially important as ships depend on a wide range of energy-driven systems, including propulsion engines, electrical power generation, and HVAC and refrigeration units. Understanding this, how energy flows and converts within these systems is essential for ensuring safe, efficient, and environmentally responsible vessel operation. So the first law of thermodynamics, when stated mathematically, this can be expressed for a non-isolated system as a change in internal energy. The first law states that delta U is equals to Q minus W. So delta U here is the change in internal energy. Meanwhile, Q is heat added to the system. So if heat is added to the system, its internal energy increases. Meanwhile, W is the work done by the system. So if the system does work on its surroundings, its internal energy decreases. So meaning, energy can neither be created nor destroyed, only converted between forms such as heat, mechanical work, electrical energy, and this principle is foundational for analyzing all shipboard systems.
The first law of thermodynamics is used in marine propulsion to track how chemical energy in fuel is converted to heat and then mechanical work to drive the propeller. Engineers apply it through control volume energy balances to major components such as engines, boilers, turbines, compressors, and heat exchangers, ensuring that all energy entering and leaving is accounted for. It is essential for efficiency calculations, helping identify where energy is used or wasted, like useful work, exhaust heat, and cooling losses. The law also supports performance and fuel consumption monitoring, ensuring the vessel's energy input matches its expected output.
Marine engines and steam turbines. The first law of thermodynamics, energy conservation, is fundamental for analyzing marine engines and steam turbines, ensuring that all energy entering a system must equal the energy leaving it. Engineers use it to perform energy balances, often with a steady flow energy equation to track how fuel energy is converted and where losses occur. In marine diesel engines, the law governs the conversion of chemical energy, heat mechanical work, while also accounting for energy losses through cooling system and exhaust gases. By applying the first law to the engine as a control volume, engineers calculate key performance measures such as thermal efficiency, ensuring that output energy never exceeds input energy.
Waste heat recovery system. The first law of thermodynamics, or the principle of conservation of energy, is applied to waste heat recovery system by conducting an energy balance. It ensures that all the energy entering the system, waste heat, is accounted for in the useful energy recovered and any remaining losses. In a sense, the first law confirms that while energy cannot be destroyed, the challenge and the energy engineering goals are convert as much of the waste energy as possible into a useful form, rather than letting it dissipate into the environment.
Electrical power system. The first law of thermodynamics, or the law of conservation of energy, apply to shipboard electrical power system by require that all energy input to the system must equal all the energy output and challenge the stored energy. It is the fundamental principle governing the entire energy conversion process. From fuel, the electricity enhance the first law of the thermodynamics, provide the fundamental accounting framework for all energy transfer and transformation aboard the ship. From the initial fuel source to the final electrical consumption and waste heat rejection.
HVAC and refrigeration system. The first law of thermodynamics governs the energy balance of a refrigeration system, ensuring that compression work input equals the heat removed from the cold space plus heat rejected to the surroundings. It is used to analyze each component. The compressor, where work increases the refrigerant's enthalpy. The condenser, where the refrigerant rejected heat to seawater on air. The expansion valves, where a pressure and temperature drop occurs. And the evaporator, where the refrigerant absorbs heat to provide cooling. Overall, the first law quantifies energy flow through each stage, determining cooling capacity and system efficiency.
First law of thermodynamics is central to naval architecture and marine engineering because it governs energy conversion and propulsion system, ensuring that chemical energy in fuel becomes mechanical work and waste heat. Engineers use it for efficient calculations and power predictions, matching engine power shifter systems, and onboard energy balancing, where total generator output most equal to total ship energy demand. It also underpins the design of heat exchangers, cooling systems, and waste heat recovery, ensuring all energy transfers remain accounted for even in areas like stability and ballasting, and energy considerations such as potential energy changes must still obey the conservation of energy.
Importance for the maritime industry. The first law of thermodynamics is essential in the maritime industry because it enables engineers to design efficient engines, perform accurate energy balances, and optimize ship systems for fuel economy and environmental compliance. It governs how fuel energy is converted into mechanical work, supports waste heat recovery to improve overall efficiency, and guides the design of key components such as boilers, turbines, compressors, and heat exchangers. The law also underpins energy audits and operational tools like EED or Energy Efficiency Design Index, SAMP or Ship Energy Efficiency Management Plan, and EEOI or Energy Efficiency Operational Index, helping ships meet modern efficiency and emissions standards.
So, in conclusion, the first law of thermodynamics is a foundational principle in marine engineering, shaping how every energy is converted, transferred, and utilized throughout a ship's propulsion and auxiliary systems, by ensuring that all energy inputs and outputs are fully accounted for. It allows engineers to design efficient engines, optimize refrigeration and heat exchange system, recover waste heat, and accurately assess vessel performance across propulsion, power generation, cooling, and environmental compliance. The first law provides the essential framework for improving efficiency, reliability, and sustainability in modern maritime operations.